Hello everyone and welcome to the webinar. My name is Josh McDaniel. I work with the Wildland Fire Lessons Learned Center, and I'll be introducing the speaker today and moderating the question and answer session. As always, I want to point out that this is a regular webinar series. It's sponsored by three organizations: the International Association of Wildland Fire, the Wildland Fire Lessons Learned Center, and the Joint Fire Science Program. And for the next couple of months, we're going to be focusing on a series of webinars that are connected, that are part of a JFSP project that was a synthesis of extreme fire behavior in a new publication that's come out detailing the results of that synthesis for field managers. And the presenter, Paul Werth, will be detailing that at the beginning of his presentation as well. But I just wanted to let you know, and there's other webinars coming up in that series, and I have them here. Paul is speaking today, Paul Werth, and he'll be speaking again tomorrow. So today's covering critical fire weather patterns for the eastern U.S., Canada, and Australia, and tomorrow he'll be talking specifically about the western U.S. In February and March, Brian Potter is going to give a series of webinars on first on fire columns and plume dynamics, and then on spot fires. Then in April, Scott Goodrick and Jason Forthofer are going to be talking about vortices and wildland fire, and then finally to end the series off in May, Marty Alexander and Miguel Cruz are going to be talking about crown fire behavior in conifer forests. Okay, so if you're not on our mailing list and you don't get the announcements and you'd like to register for those webinars, you can get there through the Lessons Learned Center webpage. This is the home page, and then if you see the icon towards the top left says Advances in Fire Practice, if you go there, that will take you to this page, which has the listing of all the upcoming webinars and links to register and that sort of thing. This is also where we post the recordings of the webinar. Every webinar is recorded and uploaded to the Lessons Learned Center's YouTube channel, and you can, about an hour after the webinar, they're ready, and you can grab the link here, pass that around to whoever you think might be interested. Okay, so one last thing just about how we deal with questions. Feel free to type your questions into the questions box in your control panel over to the right at any time. We'll hold the questions till the end, and then we'll try to work our way through the list. Usually we're able to get through all the questions or most of the questions.
On the Synthesis Volume 1 for Fire Managers, it was a publication done through a grant by Joint Fire Sciences Program. It was published in 2011, and this webinar series is a joint project of the Wildland Fire Lessons Learned Center, JFSCS program, and International Association of Wildland Fire webinar series. Okay, the presentation that I'm going to be making today is on Chapter 3. This is Critical Fire Weather Patterns of the United States, Canada, and Australia. And Volume 1 does not have the subject of Canadian and Australian critical fire weather patterns. That is going to be included in Volume 2, which is in final layout now and should be published sometime this spring. But I thought I'd go ahead and include it in this webinar series to get it out as soon as possible. The outline that we're going to be presenting here mirrors the outline in Chapter 3. We're going to be talking about weather elements that promote extreme fire behavior, and then a general discussion of critical fire weather patterns. We'll go on to regional critical fire weather patterns. We'll finish up with tools that fire managers and firefighters can use to predict critical fire weather patterns and possible extreme fire behavior. And then we'll finish up with a summary and knowledge gaps. Let's first of all define what critical fire weather patterns are. And critical fire weather patterns are the atmospheric conditions that encourage extreme fire behavior, resulting in large and destructive wildland fires. And what we're going to be talking about in this webinar here is the synoptic weather patterns. And those are the large-scale weather patterns that cover 1,000 miles or more. And so we're not going to be talking about local effects, for instance, local winds, slope, canyon winds, sea breeze fronts. The webinar 2 weeks ago covered local winds and canyon winds in a webinar called Effects of Complex Terrain on Extreme Fire Behavior. And what you're seeing on the graphic here is a 500 millibar pressure map showing a low pressure trough off the west coast of the United States, an upper ridge up through the western United States into Canada, and then another large trough over the eastern portions of Canada from Hudson Bay down into the Great Lakes. And these systems these systems typically move from west to east, and sometimes they move more north and south. When they move west to east, we call that zonal flow, and north to south movement is more meridional flow. Now let's first review what weather elements promote extreme fire behavior. And there are 4 of them: low relative humidity, that's low atmospheric moisture; strong surface wind; unstable air; and drought. And from all the research that I've seen, all the literature, low relative humidity is common in just about every example of extreme fire behavior. Strong surface wind occur together, but that's not necessary. It could either be one or the other. And drought can also be a factor or a non-factor. But when all of these 4 factors work together, tend to have the most extreme fire and weather conditions. Let's review low relative humidity. It lowers the moisture content of fuels, especially the fine fuels that are easier to ignite and carry the fire. It increases spotting potential, and one thing that has come out through the literature, there are regional RH thresholds for extreme fire behavior. As early as 1928, Stickle identified 40% RH threshold for Massachusetts. Overall, the threshold can range from 10% to 40% depending on the fuel model. And in Florida, for example, in 1998 wildfires, 30 to 40% was really the threshold that we as forecasters use there. Strong surface wind supplies oxygen to the fire, increasing intensity. It preheats the fuel as the flaming front bends over the fuel bed. It increases rate of spread, increases downwind spotting, and produces wind-driven fires. Unstable air enhances upward vertical motion, supplies more oxygen to the fire, enhances vertical growth of the smoke column, also increases chance of gusty winds and vortices. Plume-dominated fires occur more often when the air is unstable. And Brian Potter, in a future webinar, will be talking about plume dynamics. Unstable air produces Haines Index values of 5 and 6, and there is a possibility of dry lightning in unstable air. Drought lowers the moisture content of both the live and dead fuels. It affects fuel availability, that is the loading and combustibility of the fuel bed. And the picture on the right here, you can see a lot of down large fuels. This is where effects of drought would really affect the flammability of those fuels, and also the surface fire intensity produced by those fuels. And drought is not always a prerequisite for large fires. For example, many of the range fires in the western United States occur when we're actually in a moist period and drought is not an issue. Okay, reviewing some of the early literature on synoptic weather types associated with critical fire weather. Schroeder and a host of others in 1964 really brought this to the forefront in their very extensive publication, Synoptic Weather Types Associated with Critical Fire Weather. And they looked at both the upper air patterns and surface patterns, divided the United States into 14 regions, and looked primarily at what patterns produced high to extreme fire danger, and also looked at large fires to see what conditions those large fires burned under. And for the area east of the Rocky Mountains, their conclusion was that most critical fire weather patterns are associated with the periphery of high pressure areas, particularly in the prefrontal, frontal, and postfrontal areas. Another early publication and research project was by Brotak and Schneider in 1977, and they wrote a paper on predicting major wildland fire occurrence. And in that project, they analyzed 52 large fires in the Great Plains, Great Lakes, and eastern United States, and plotted the time of greatest growth with surface and upper pressure patterns. The graphic on the lower left-hand side here is a idealized surface chart with all the fires that they studied, plotted in relation to a surface low-pressure center with a trailing cold front southward, and the low-pressure system was embedded in between a high pressure to the south and east and another high pressure to the west. And they also showed a warm front coming from the low pressure eastward. Now this was actually taken from their publication, and the way they demarked the different fires that they looked at, those that are plotted with an open triangle were fires that followed cold front passage. So they were post-frontal. And you can see along the idealized cold front here that all of those fires are just really just behind the cold front or just a short distance further back. Those demarked by a solid circle were fires that preceded a cold front passage, and they were just right in the vicinity ahead of a cold front. There were two other types of classifications they gave. A plus symbol was a warm sector of the surface low. There's a cluster just south of the warm front. And then the last category they had was warm sector of surface high, which is an open square. And those are located near the surface high pressure areas. Anyway, what they found out was looking at these 52 large fires, the area just prior and after the passage of cold fronts were the favored areas for large fires. Looking at the 500 millibar chart on the right-hand side here, these same fires are plotted on that chart, and this area here is the upper ridge, and the upper trough is back to the west here. And the bulk of the fires are situated between the upper ridge line and the upper trough line. And I think about 70% of those lie between the upper ridge and the trough. Okay, looking at some regional critical fire weather patterns now, we're going to look at the northern plains, Great Lakes, and the northeastern United States. And for that area is shown on the map to the left here. It's primarily from Minnesota and Missouri on eastward along the Ohio Valley into the northeast. Fire season there is basically prior to green up in the spring and after leaf leaf drop in the fall. The months it can start in early March in the northern plains, Minnesota, and in the Dakotas, and then in the Ohio Valley, also March to early April. And we get into April and May, it's in the Great Lakes and the Northeast. Fall fire season can last as late as late November. Okay, the regional critical fire weather patterns for these areas are primarily identified by the source of the surface high pressure area before or after the passage of cold fronts. There are three of them. The Pacific High originates over the Pacific Ocean and loses much of its moisture as it crosses the Rocky Mountains. The northwestern Canadian High originates in northwest Canada and becomes warmer and drier as it moves southeastward into the United States. And probably the most important one here is the Hudson Bay High. Originates in Hudson Bay area and produces unusually low relative humidity as it moves southeastward. Dry cold fronts at the leading edge of this high pressure system can produce extreme fire behavior. This graphic here shows the origination of these high pressure areas. The Pacific High originates over the Pacific Ocean, which has a temperature, let's say, in the upper 40s to low 50s. So dew points in this air mass here would start at about upper 40s, low 50s, moves inland across the west coast and the Rocky Mountains, and loses some of its moisture. But as a rule, the dew points and relative humidity stay a little bit higher than those that originate in Canada. The Hudson Bay High originates in an area that is probably still snow and ice covered in April and May. So dew points in this area are probably in the 20s, maybe low 30s. And so the air already starts off quite dry as it moves southeastward into the Great Lakes area. It warms up and the relative humidities drop quite a bit, becoming critically low. So this is one reason why the Hudson Bay High is probably the most critical pattern for the Great Lakes and the northeastern part of the United States. A fire case study that we're going to look at is the Bass River Fire, which burned in New Jersey on July 22nd, 1977. And looking at the graphic on the left here, this is a surface high pressure area. It's a Hudson Bay High. New Jersey and the fire area is located right about in this area just south of New York. The fire was in an area called the Pine Barrens, and so that is a high fire prone area just due to the type of pine trees and the needle drop. Also, the soils there are quite sandy, so they don't retain as much moisture as other soils do. So the fire was located in the southern part of New Jersey. Cold front had moved through that area previously and was situated out over the Atlantic Ocean. Anyway, this fire started the afternoon of July 22nd, 1977. It rapidly transformed into an extreme fire behavior situation. There were 4 firefighter fatalities, and it was characterized by this strong pressure gradient between the cold front and the high pressure area. These lines here, the isobars, tightly packed, so the winds were quite strong from the northwest at 20 miles per hour and possibly higher, and the relative humidity was unusually low at 27%. Unstable air was also a contributor, and there was a long-term drought in that area. So looking at the weather elements that promote extreme fire behavior, we had the strong winds, the low relative humidity, the unstable air, and the drought. This is an example of a classic post-cold frontal passage, and it occurred on the southeastern quadrant of the Hudson Bay High. Another fire example in the Great Lakes is the Mack Lake fire in Michigan, which burned on May 5th, 1980. And the fire was located in the upper part of the lower peninsula of Michigan. It was actually a prescribed burn to enhance the habitat for the Kirtland warbler bird, and the folks that lit that thought they were in prescription, but little did they know that a dry cold front would be coming through that afternoon. Anyway, they started igniting the prescribed burn very rapidly. They had problems with spot fires and transitioned into extreme fire behavior very rapidly. There was one firefighter fatality. There were strong southwest winds, 15 to 25 miles per hour, prior to the cold front moving through, and then those shifted to the northwest. There was also unusually low relative humidity, as low as 24%, and unstable air was associated with the dry cold front as it passed. So we had the strong winds, the unusually low relative humidity, and the unstable air. Drought did not seem to be a critical factor in this particular fire situation here. But this was a classical prefrontal critical fire weather pattern. The southeastern United States involves from Texas and Oklahoma, south of the Ohio River Valley, to the Atlantic Gulf Coast down to Florida and along the Gulf Coast itself. Fire season here is primarily during the spring and fall, but can occur at other times of the year also. Starts usually in March near the Carolina coast down to Florida and across the Gulf Coast region. The fall season also lasts through November, and February you can see large grass fires in Oklahoma and Texas, so this area here can experience fire season throughout much of the year. Regional critical fire weather patterns for this area, there are three. Strong westerly flow, this is during the spring and fall. Strong westerly jet stream winds aloft result in a rapid succession of cold fronts with little if any moisture. The second pattern is northwest flow, and this is dry air associated with Canadian high pressure systems. Again, very similar to the northeastern and Great Lakes state, Hudson Bay high, and northwest Canadian high pressure systems. The key factor here is that air is being drawn into this region from the Great Plains or central Canada, and that is results in unusually low relative humidity and also accompanied by strong gusty winds, especially after the cold front passage. And a third critical fire weather pattern occurs when high pressure aloft near the Atlantic coast blocks weather systems from entering the region for an extended period of time. And this is probably a long wave ridge that sometimes develops over the eastern part of the United States and can last for weeks at a time. And this is particularly evident in the fall when we start to have deal problems with leaf drop. Fire case study for this region is Florida fire siege in 1998. 500 millibar chart is on the left-hand side of the graphic here, showing a upper-level trough over the northeastern part of the United States down into the mid-Atlantic states. And the southeastern U.S., including Florida, is getting a flow of air from the Great Plains, as indicated by this blue line here. This is where the air was coming in for a good portion of the fires during June and July of 1988. Because of this dry air and occasionally gusty west to northwest winds, we experienced extreme fire behavior on many days during this 2-month period. Long-term drought also came into play here, affecting the severity of the fires. Many days we had unusually low relative humidity, less than 35%, and On these fires, I noticed that once the relative humidity got down to 40%, fires activity started to pick up. And if it made it down to 35%, the fires were really showing some effects of extreme fire behavior. Also during this time period, due to the dryness of the air and the fact that we had a lot of low-level instability, Haines Index values were often 5s and 6s. And again, the source of this dry air was from the Great Plains. The next graphic here shows the smoke columns along the east coast of the Central Florida Peninsula. This was on July 1st, showing all the large fires being driven by strong westerly winds aloft. Okay, the next area we want to deal with is critical fire weather patterns in Canada. And probably one of the primary literature for critical fire weather patterns, in my estimation, is done by Nick Nimchuk in 1983 in his publication, Wildfire Behavior Associated with the Upper Ridge Breakdown. Now, this was the first time Upper Ridge Breakdown was coined, so I think he was really keyed in on the upper level patterns. Now, Nimchuk studied wildfires during the severe 1981 Alberta fire season in relation to 500 millibar and surface pressure patterns. A part of this research, he identified the lifetime cycle of an upper level ridge as 3 distinct fire weather stages, and summarized that he thought clearly identified the breakdown rather than the presence of the upper ridge as the trigger to extreme fire behavior. This next slide here shows his lifetime cycles of the upper level ridge. The graphic on the right here shows a large high pressure center over southwestern United States with the ridge extending on up into southern Canada. And the first stage was classified as the establishment stage. This is where the upper level ridge was building into an area after the passage of an upper level trough. What you have here with building high pressure, heights are rising, warming air aloft, which is a stabilizing effect. So the establishment period he categorized as being warm and dry, yet had very stable conditions. It could have low relative humidity, light winds. The fuel moisture would be decreasing during this stage, and there would be a low lightning risk due to the stable conditions. His second stage was classified as the initial weakening, and that is depicted by this red dashed line here, wheat trough moving in over the top of this stationary ridge over the southwestern United States. In this initial weakening, the air becomes more unstable. There's a little bit of cooling aloft that takes place, so the atmosphere is becoming more unstable. Increased lightning activity would result in more wind, usually due to more winds aloft, and continued low relative humidity. And finally, in the final breakdown of the upper ridge, you have a stronger trough that moves into the ridge and actually flattens it completely or moves it to the east. And this is the point where you have cold front passage, unstable air, lightning, strong shifting wind, low relative humidity initially, but increasing after frontal passage. Now the schematic here, a breakdown of the upper level ridge, includes both the upper level pattern with the lower surface pattern superimposed underneath that. And that's in this graphic showing the solid lines are the upper level pressure pressure patterns, surface high over the Four Corners area of the United States. Appears to be a trough moving in from the Pacific coast. At the surface there would be a surface thermal trough, typically develops over the southern Colorado Basin and extends northward into California. And when a trough moves in from the Pacific Ocean, that gets shifted eastward into the Intermountain area and the northern Rockies. So you have that going on at the surface. And then this arrow of dry air here, that refers to, in the water vapor imagery, dry slots, an area of dark, dry air that shows up in water vapor imagery. And that is important in realizing that you have low atmospheric moisture that could be working its way down to the surface. So with all that in mind, the breakdown of the upper level pattern, upper level ridge, produces unstable air mass due to cooling aloft. Unstable air increases the chance of thunderstorms and dry lightning. Strong surface winds could be due to a jet stream aloft and the downward momentum of winds aloft that reach a surface. Also characterized by hot temperatures, low relative humidity, moderate to high Haines Index, and often a thermal trough or cold front at the surface. So when you look at all the characteristics that air mass has during the breakdown of the upper level ridge, there's everything there to produce extreme fire behavior. Now the Canadian case is one that Nimchuk illustrated in his publication here, and it has to do with the August 27th, 1981 severe fire situation that broke up in northern Alberta in this red circle area here. That's where the fires were located. In the 500 millibar pattern showed the semi-permanent high pressure over the western United States during the summer, extending northward into the prairie provinces of Canada and actually hooking up with the interior high pressure center over Alaska. Approaching the west coast was a rather strong low pressure center for this time of year. And you can see there's a lot of gradient across the Canadian Rockies into Alberta between the high pressure ridge and the low upper level low pressure system. At the surface, there was a surface low pressure center in the northwest corner of Alberta with a cold front extending southward into western Montana, and a tremendous amount of gradient across that, indicating there was a distinct thermal gradient across the area there, which resulted in strong winds. And what this fire situation experienced was extreme fire behavior, strong south winds. This was a prefrontal wind to start off with, 40 to 65 kilometers per hour. Unusually low relative humidity, it was 30%. These fires in this particular day burned 376,000 hectares. Upper level and surface pattern exhibited strong temperature and pressure gradients. And this was the classic breakdown of the upper level ridge that Nimchuk used to illustrate his research. Now, additional Canadian literature, Newark, 1975, published a paper called The Relationship Between Forest Fire Occurrence and 500 millibar long-wave ridging. And he studied the 1974 long-wave ridge that was stationary over northwestern Ontario for about 55 days during the summer. And he showed that this ridge, long-wave ridge, broke down about every 11-day period with minor troughs moving over the top of it. But overall, the ridge itself lasted for 55 days. Close relationship existed between the time of occurrence of peaks in the long wave ridge and the times of high fire danger or high weather index. Another publication was done by Skinner and others, 500 millibar synoptic wildland fire climatology for large Canadian forest fires. And basically he looked at strong meridional flow, high pressure ridge over western Canada as being the prime pattern for large fires. Okay, and finally we're going to look at critical fire weather patterns in Australia, the breakdown of the Upperlevel Ridge. For Australia, a graphic on the right here shows the progression of fire seasons starting in the north during the winter and spring and progressing southward into the fall and autumn down in the southern portion of Australia. Now Mills wrote a paper on the meteorology of the Ash Wednesday 1983 fires. So we'll be looking at weather pattern associated with that. But Mills in his paper identified the surface and 500 millibar patterns during the severe fire spread. And looking back at analysis of 40 years of data, he showed that the 850 temperature gradient, 850 millibar temperature gradient on Ash Wednesday was extremely strong, the third strongest ever occur in February and the 10th strongest over the summer months. And he concluded that that was one reason, the temperature gradient, that caused such extreme fire behavior problems there. Now, the weather charts associated with this Ash Wednesday incident on the left-hand side here of the slide. This was the 500 millibar pattern that was in place just prior to the start of these fires. And you can see that a large high pressure aloft, that's a very strong one, was centered over the interior of Australia, with the Upperlevel Ridge extending southeastward from that out east of Tasmania. At the same time, there was a strong upper-level trough that was moving eastward through the Southern Ocean and was just starting to impact the Victoria area in southeastern Australia. The surface pattern on the right-hand side here shows a surface low-pressure center just to the west of Tasmania, with the cold front extending northward into the interior of Australia. And ahead of this front there were very strong northwest winds, surface winds, that were moving across southeastern Australia. Again, this was the Ash Wednesday severe bushfire incident, February 16th, 1983. Extreme fire behavior was prominent. There were 75 fatalities, strong prefrontal northwest winds, unusually low relative humidity, significant long-term drought, upper-level surface pattern, exhibited strong temperature and pressure gradients, and this was a classic breakdown of the Upperlevel Ridge pattern. Additional Australian literature can be found in Long's publication, The Climatology of Extreme Fire Weather Days in Victoria. Looked at different synoptic patterns and found that about 72% of the events occurred with winds from the north, which are typically hot and dry, having originated in central Australia. Bannister also has a publication modeling challenges from the Black Saturday 2009 event, and I have a link posted there. And then also Mills has meteorological drivers of extreme bush fire events in southern Alaska with the link there. Okay, for predictive tools now, there are products being produced by both the National Weather Service and the Geographic Area Coordination Center Predictive Services units that can be used to highlight areas potential extreme fire behavior and large fire growth. The predictive service products listed on the left-hand side here, the National Wildland Significant Fire Potential Outlook is issued once a month, usually the first business day of the month. Have an example of the current one on the right-hand side here, showing that in April and May, the Great Lakes and Ohio River Valley, Upper Mississippi River Valley are highlighted for an area that could be very active fire situation this spring. Other products include the 7-day significant fire potential, which is produced once a day during the fire season, fuel and fire behavior advisories, weather and intelligence briefings during the fire season, situation reports, and resource summaries. The National Weather Service also produces some products that are very useful for determining areas' potential large fire growth and extreme fire behavior. The graphic on the left here shows red flag warnings from July 22nd, 2014, highlighting areas where fire weather patterns are critical for large fire growth and extreme fire behavior. Other products beside red flag warnings are spot weather forecast, fire weather watches. Storm Prediction Center puts out some fire weather outlooks on a daily basis. Local National Weather Service offices do web-based fire weather briefings during the fire season. And there are also FarSight data streams available on most Weather Service web page. Okay, to summarize here, tracking the development of critical fire weather patterns is essential in identifying days when large wildland fires exhibiting extreme fire behavior are most likely to occur. And something I would reemphasize that firefighters can do in the field is one, know what the relative humidity thresholds are in their area for active fire behavior, and then also monitor the relative humidity at the site there. More research is needed to determine the frequency at which these critical fire weather patterns occur. We definitely need more research to understand the dynamics of these critical fire weather patterns. For instance, the thermal gradients and identifying when one critical fire weather pattern may be more detrimental than others. And then finally, a way to include atmospheric stability as an input into the fire behavior models. Right now, we know atmospheric stability is an important factor in the development of extreme fire behavior, but all we have is just the subjective reasoning behind that, no objective tools. Additional information at links. I've included here a publication by the National Weather Service. It was a fire weather training report called Critical Fire Weather Patterns in the United States. There is a link to that, and that will take you to the Northwest Interagency Coordination Center in Portland. And then also recently the Desert Research Program for Climate, Ecosystem, and Fire Applications, CEFA, has a critical fire weather pattern project, and I included the link to that. And this has many more cases of critical fire weather patterns and some really good graphics in that. So that's all I have, and now I would entertain questions. Okay, I seem to have lost Josh. And I have one question here that says, I think you lost Josh, Paul.
Paul, can you hear me now?
I can hear you now.
Oh, okay. Man, the webinar gremlins are coming after me today.
Well, I lost you at the introduction, and I just kind of started winging it.
Yeah, I gave you this glowing introduction, then I realized nobody could hear me. So I was rambling on there for quite a while before I realized nobody could hear me. Okay, well, I apologize
about that. Well, I hope we didn't confuse people. And
I apologize to the audience there. I'm not sure quite what happened there. But we do have a few questions that have come in. Start going through there. Brian Potter asks, Paul, not so much a question as a comment, but can you say something briefly about what makes these patterns cause extreme fire behavior and how we define extreme fire behavior in the synthesis?
Okay. Okay, in the synthesis, we came up as a collective definition by all the different authors, chapter authors, and we wanted to clarify what extreme fire behavior was, to simplify it. And our definition was fire spread other than steady state surface spread, especially when it involves rapid increase. So we're looking at any kind of fire behavior that is beyond surface spread, that's crowning, spotting, and rapid rates of spread. And these critical fire weather patterns affect extreme fire behavior because of the effect of relative humidity. And we know relative humidity affects the rate of spread. It's one of the primary inputs into the fire behavior prediction system. So when you have unusually low relative humidity for your area, your fire is going to be more intense. It's going to have more rapid rate of spread, especially if you put some wind on that flaming front. You're going to have spotting. Strong surface winds, that's kind of explanatory, but a breakdown of the upper level ridge, I think, is really the primary critical fire weather pattern we have. And a lot of times we see that in a breakdown of an upper level ridge, it involves an upper level jet stream, and you have, due to the instability also included in there, downward momentum of these winds can hit the surface, impact the surface winds also, increasing them. And unstable air just affects the plume dynamics. And Brian, that's your chapter. But there's a whole range of things that plume dynamics affects on a fire front, from the supply of oxygen and spotting potential and potential for vorticities.
Okay.
So that was a good question, Brian.
All right. The next question is from David Fenn, and he asks, your slide showing the initial breakdown stage, would you characterize that as being conducive to dry lightning?
The key, I would say, would be inducive to dry lightning. The key there is how much moisture is getting into the air mass there. And the water vapor imagery can help to see where that moisture is coming from. For instance, in the eastern United States, if you get a flow of air that originates from the Gulf of Mexico, where you have dew points and water temperatures in the 70s, or in the Atlantic Ocean, where you have the Gulf Stream producing very warm and moist air, that's going to provide so much water vapor into the atmosphere that in those cases you would not have dry lightning but wet lightning, and that's what you mostly see there. But I think in the initial weakening, It really depends on the orientation of the trough, where the air is being entrained into the trough, if it's coming from a moist region or a dry region. Those things that are really unique to each small upper level trough that involved in the initial weakening.
Okay. The next
Another
question.
Good question.
Then the next question is from Gary Curcio. Is the breakdown of the upper ridge the same as Brotac's presence / the position of the upper level 500 millibar trough within the, oh, this one's getting a little technical for me to read. Let's see. So he's wanting to know if is the breakdown of the upper ridge the same as Brotac's presence / the position of the upper level 500 millibar trough within. Maybe you should read this one out loud, I think. Then plus or minus 400 miles and its radius of curvature.
Okay.
Less than 400 miles. This can lead to extreme fire behavior. Can you see that one?
Okay, let me go down here and take a look. I don't see that one, but I hope I can answer Gary's question. In the slide that I showed Brotac and Schneider, they showed the relationship to the upper level pressure pattern of the 52 fires that they investigated. And the vast majority of those fires, I think I counted up, there were like 70% plus, were between the upper ridge line and the upper trough line. And that is the area that is a breakdown of the upper level ridge. And I think most critical fire weather patterns are going to be a breakdown of the upper level ridge. Now, along the eastern coast, most of the large fires there occur after the passage of the cold front and oftentimes after the passage of the upper level trough. So they fall outside of the boundary between the upper level ridge and the trough. And that is because the proximity of when the breakdown of the upper level ridge occurs, especially from the area of Appalachian Mountains to the Atlantic coast, the air is being advected northward from the Gulf of Mexico. Very moist, high dew points. And so to me that is not a critical fire weather pattern in the sense that it doesn't really classify as unusually low relative humidity. The critical fire weather pattern for that part of the country, for instance the Carolinas, Virginia, is after the upper trough moves to the east and you start getting a trajectory of air from plains or Canada. And so I think along the east coast there, the level ridge breakdown is probably not that critical. It's more post-frontal and post-upper trough because you need that unusually low relative humidity. And you're not going to get that from the Gulf of Mexico or from the Atlantic Ocean. I hope that answers your question, Gary. Okay.
And sorry, Gary, if I butchered your question there. If I didn't, just send in maybe a different version, and we'll see if we can get that answered. The next question is from Rich McCrae. This is an observation. He says the effects of widespread regional smoke from wildfires is also important and impacts other fires. Anything you want to respond to there?
That can happen. In fact, I was on a fire in central Idaho. This was probably in the 90s, 94, 96, one of those big years. And we had quite a large fire, but we had a new fire that started to the southwest of us, our particular fire, and put up a huge smoke column and shaded our fire, and provided enough shade where fire behavior was not that pronounced, just due to the shading from the smoke column from the other fire. The relative humidities were higher, the temperatures were a little cooler, and so yeah, smoke from other fires can affect fire behavior on surrounding fires.
Okay, this is another comment. This is from Nick Nimchuk. He says, excellent presentation, Paul. We can never overstate the importance of pattern recognition and relative humidity in the fire weather business.
And I agree with Nick completely on that. Like I said, I think he has had one of the landmark publications in this whole critical fire weather topic here.
Okay. Another question from Gary Curcio. Instability is important, but in the south, isn't dryness aloft more critical, or a higher weighing factor or influence more so than instability, and why?
Again, that has to do, and I think his statement is correct there. And I think it's because a lot of the fires in the south and in the east are post-frontal, because the low relative humidities being transported from the Great Plains or Canada affect the flammability more than this unstable air. Behind the cold front, you're going to have more stable air. So the Haines Index isn't going to be as high behind the cold front, and dryness of the air is going to be more of a factor. Now, in the case of the Florida fires, when the Haines Index is high, you can have explosive fire behavior. The case I showed was July 1st. I happened to be on those fires in central Florida, and that was a very explosive day, and the upper air soundings in Florida all showed a low-level Haines Index of 6 that day. So it can happen, and when that happens, that just adds more conditions favorable for extreme fire behavior.
Okay.
So I think that's all I have to say. I agree with Gary on that point, just due to get the low relative humidities, you need the air from the interior of the country, post cold front, post upper trough, and that's going to be more stable air.
Okay, next question is from Greg Murdoch, and he asks, in your estimation, would there be any value in looking at Haines Index in terms of real lapse rates instead of the poor man's lapse rates, the temperature difference as is used now?
Well, you know, the Haines Index is a very crude measure of instability in the atmosphere that pertains to wildland fire. And the reason Haines did that is he wanted to look at something that would be easily calculated in the field using the readout from the upper air soundings in the area there. So he looked at distinct values, distinct levels for calculating the Haines Index. And there are some problems associated with that. For instance, my brother and I, John Werth, did a climatology of Haines Index values for the western United States. And in the interior of the western United States, the surface heating is so intense during the day that what it did is it raised the mixing height or the boundary level up through the 500 millibar level and created a very steep lapse rate that was not a function of any atmospheric patterns, but just due to the surface heating. So day in and day out you would get a Haines Index 6 just because of the distinct levels that Haines designed his index on. Another example is California, where the marine layer tends to limit the amount of mixing during the day there. Haines identified that area as part of the high Haines Index region, but the mixing never came anywhere close to what was happening at the 700 to 500 millibar lapse rates. So California oftentimes has 5s and 6s, and they don't have any problem there. So there are problems with the way the Haines Index is calculated, but I know Brian Potter has done some work on that, but there really has been no alternate way of calculating that. To me, that's another prime area for research. Hope that answered your question.
Okay, so the next question is from Nick Nosler. He says, some of these patterns occur throughout the year. Is there any research that establishes thresholds of atmospheric and fire danger values that would make a pattern critical?
Well, that's a good point. And right now I don't see any literature that points to that, except I'm currently working on a series of papers that looks at 500 millibar heights over a 10-year period in Washington and Oregon, and does a daily timeline with the addition of new large fires. So for instance, each day I'm tracking the 500 millibar heights over Washington and Oregon during the summer. June through October is the fire season. And I'm plotting the 500 millibar height for that day, plus also the number of new occurrences of large fires. That's 100 acres in timber and 300 acres in grass. And I've published the first paper in that series on my website, fireweather.com. Just look under what's new. But I'm probably going to have 5 or 6 different papers on there. And one thing, there's a very strong correlation to the occurrence of large fires. Could be inferred that's extreme fire behavior, but there's a very strong correlation, better than 0.95, to the 500 millibar heights. And I see threshold of about a 580 millibar height. If you get below that, the frequency of large fires really decreases. Above that, really increases. So yes, there is a threshold there, but I'm pretty sure it's going to be different for different areas of the country. And I'm only looked at Washington and Oregon. And certainly time of season is a critical factor too. I look at what is typically the fire season. For instance, in the winter we can have heights that are above 580, and of course we're out of fire season. Again, what is happening in the upper atmosphere really doesn't affect down to the surface in the wintertime. So I would say look at your fire season, and definitely the strength of the 500 millibar ridge and the depth of the upper trough moving in or breaking down that 500 millibar ridge is critical. And yes, I do believe there are thresholds for that, but not much literature on that at all. And I haven't published that paper yet. That's probably 3rd or 4th down the line. Okay, that's a very good question.
Next question is from James Cook, and he asks, a good deal of discussion was on relative humidity, but without mention of crossover conditions. Is relative humidity more predictive even without crossover conditions?
What kind of conditions were those?
Crossover conditions?
Crossover?
Yes.
I'm not sure I understand the question of what he means by crossover conditions.
Okay.
Maybe,
James, if you're still on, maybe you can clarify, and we'll see. Let's see if he.
yeah, I see
clarify.
his question there, but
When temperatures exceed RH. That's a Canadian term, David Finn says.
Oh, okay, Canadian term. Well, I'm not an expert on Canada. I've read a lot of literature, but I'm not an expert on Canada. I'm just reading over the question again, trying to clarify this in my mind so I can give him at least a somewhat of an answer that will address what his intent here is. Okay, looks like he's talking, asking is RH more predictive even without crossover conditions? And I'm going to answer this, but I don't know if I'm going to completely satisfy his question. Relative humidity is easy to measure in the field, and when I would be an incident meteorologist going out to fires, one of the first things I would do is I would get to crews or operations people and find out, one, when the fire behavior really picked up and what the relative humidity was at that time. So what I was trying to do was develop a threshold for that particular fire, relative humidity predictor. And I found that to be a very good tool in preparing my briefings and also my forecasts for the operational shifts, is to first of all identify what the critical RH was on that particular fire and the time I thought that would be achieved. And I would say that the fire behavior would pick up significantly when that relative humidity threshold was reached, oftentimes even before the surface wind picked up, or even before, the surface wind may never have gotten strong, but if the relative humidity dropped below that threshold, fire activity and some form of crowning often would happen at that point. So I guess the bottom line here is I would not tie wind speed to the relative humidity. I would look at them separate because they are different. So relative humidity in my mind is more important and probably easier to predict and measure.
Okay.
I hope that satisfied him. If not, we could certainly send me an email on my website, and we can discuss this further.
Okay. Next question is Rick McRae. He says, in Australia, Michael Reeder looked at overturning Rossby waves and their role in bad fire days. Has this been looked at in America?
I've seen some literature on Rossby waves, but really not so much on how they affect wildland fire. So if that research is being done in Australia, that probably is something we should be looking in the United States and other countries too.
Okay. Jay Charney asks, can you offer some insight into how to distinguish between elevated fire weather and extreme fire weather? To me, most of what was discussed here does not necessarily promote extreme fire behavior, but rather most of the discussion is concerned more garden variety fire weather conditions. Can you say how often do extreme conditions actually occur, and under what scenarios are those conditions actually predictable?
Okay, when I started this, I said we were going to look at synoptic patterns, which are the large-scale weather features, high pressure, low pressure areas, jet streams, that sort of thing. But you have to realize also that extreme fire behavior can be produced on a very local level due to local winds, different aspect conditions. Certainly south aspects have hotter, drier conditions, more wind than north aspects. So there are a lot of local conditions that can produce extreme fire behavior that are not included in the critical fire weather patterns. And when the study of critical fire weather patterns has gone on for 50 years now, and most of that research has been done looking at specific critical or specific large and destructive wildfires. So there hasn't been research to see how these conditions affect day in and day out. They're somewhat skewed on the fact that the research has been conducted on large destructive wildfires, those that make huge runs, crown fires, fatalities, and such. So there has not been the research done to see how day in and day out how these critical fire weather patterns would affect, for instance, the really extreme conditions or more of the daily conditions. To me, that's another area of research that needs to be done. But certainly in the breakdown of the upper level ridge, the dynamics there, when you look at the unstable air, the strong wind potential, and the low relative humidity, that would certainly exacerbate any kind of burning conditions up into the extreme category. So, okay.
Okay. Next question, another one from Gary Curcio. With the Haines Index, should it be regionalized by weighing the stability and moisture sides of the equation with different weighting? For example, in North Carolina, a critical Haines Index starts at 4, not 5 or 6.
Yeah, I have seen modifications in different areas of the country, and like I said, there really needs to be a coordinated effort nationally to revise the Haines Index. I think the concept is good, but again, personal conversation with Don Haines, he wanted something that was easy and to calculate and would be very broad scale. So I think that there are definitely mechanisms and regionally to modify that, and I know some areas, some regions have done that. So I would say if something works in your region, go with it.
Okay. Todd Lindley asks, any thoughts on importance of temperature anomalies, i.e. West Coast thermal trough or Southern Plains thermal ridge, in influencing extreme fire in these patterns?
Yes. In fact, tomorrow I'm going to be talking about a case in West Texas called the dry line. and that is really kind of fits into the thermal troughs. It's really a demarcation of dew point, but it is kind of in the same framework as the thermal trough, how it develops in California and southern Arizona, and then depending upon the upper level pressure pattern will push north into Washington and Oregon and then shift east of the Cascades. So there is ongoing research on looking at the surface thermal trough, which I think for the West Coast and the Intermountain West is very important, and a situation that acts very similar to cold fronts back east. So tomorrow we'll be talking a lot about thermal troughs and also dry lines.
Okay. Gary Curcio asks again, wind profiles, low-level jets, or reverse wind speed profiles have been critical in flat country. At what upper limit, or in meaning altitude, would you consider a low-level jet point where the increased wind speeds lose influence with surface fires?
Well, most of the cases I've seen of low-level jets have been, 2,000–3,000 feet off the surface. And certainly there are jet maxes. You can carry it all the way up to 10,000, 18,000 feet that never reach the surface. So I think on the jet maxes affecting fire behavior, especially in flat ground, is probably a matter of a few thousand feet off the surface. That's most of the examples that I have seen.
Okay. And I think that does it for the question. Oh, sorry. Go ahead.
Okay.
I didn't mean to interrupt you, but if you still had something.
Oh, that's okay. I was just going to add to that last question that the stability of the air mass also would determine the depth at which that low-level jet could be brought down to the surface.
Okay. And then the last point, Brian Potter points out that the breakdown of the upper level ridge is essentially a breaking Rossby wave.
Okay.
All right.
Good point.
Well, that is it. Thank you, Paul. That was a lot of questions to work through there. And Paul's going to be doing this again tomorrow, focusing more on the western U.S. And so same time, same place, and hopefully my audio will be working so you guys will be able to hear that glowing introduction that I give of Paul tomorrow. All right, thanks, Paul. That was a great job.
Okay,
And thanks,
thank
everyone.
you.
And thanks, everyone, for coming.